Hey there. Today, we're going to dive into the world of hydrocarbons, specifically focusing on three important classes: alkanes, alkenes, and alkynes. By the end of this video, you'll be able to identify each of these groups by their chemical structure and understand the fundamental differences in their bonding. These distinctions are foundational in organic chemistry, and getting a handle on them now will make a lot of other concepts much clearer. Think of this as getting to know the core building blocks of so many organic molecules. First off, let's establish what all of these have in common. They are all hydrocarbons. As the name suggests, hydrocarbons are organic compounds made up of only two types of atoms, hydrogen and carbon. So, no oxygen, no nitrogen, just carbon and hydrogen. This simple composition makes them incredibly versatile, and they're the basis of fuels like gasoline and natural gas, as well as many plastics and other materials. Now, a key concept we'll be using is the idea of saturation. You might have heard this term before, especially with fats, like saturated fats or unsaturated fats. In chemistry, saturated has a very precise meaning. A saturated hydrocarbon is one that contains only carbon-carbon single bonds. It's saturated in the sense that the maximum number of hydrogen atoms are attached to its carbon backbone. In other words, every carbon atom is holding on to as many hydrogens as it possibly can. Let's take a quick moment to think about why this is. Carbon atoms typically form 4 bonds to be stable. If each carbon is connected to other carbons with only one single bond, it has 3 other spots left for bonds. In a simple hydrocarbon, those 3 spots are filled by hydrogen atoms. So it's saturated with hydrogens. Okay. With that foundational idea of saturation, let's meet our first class of hydrocarbons. The alkanes. Alkanes are the simplest family of organic compounds. As you might guess, they are the very definition of a saturated hydrocarbon. Alkanes are defined by containing only carbon-carbon single bonds. This single bonding makes alkanes very stable and relatively unreactive compared to other organic compounds we'll see later. There's also a general formula we can use for any straight chain or branched alkane. It's C subscript NH subscript 2N plus 2. Here N represents the number of carbon atoms. This formula is a direct consequence of every carbon being saturated with hydrogen. Let's look at an example. The smallest alkane has 1 carbon atom, so N equals 1. Plugging that into our formula, we get C1H2 times 1 plus 2, which simplifies to C1H4. This compound is called methane, the primary component of natural gas. For 2 carbons, N equals 2. The formula gives us C2H6. This is ethane. Let's draw its structure. You can see each carbon is bonded to 3 hydrogens and 1 carbon, making 4 single bonds in total for each carbon. So just to recap, alkanes are the most basic saturated hydrocarbons, defined by all single bonds and their specific formula. Now, let's explore hydrocarbons that are not saturated. These are known as unsaturated hydrocarbons. This simply means they have less than the maximum number of hydrogen atoms for their carbon backbone. Unsaturated hydrocarbons are characterized by the presence of carbon-carbon multiple bonds, either a double bond or a triple bond. This is what makes them different from alkanes. Because they have these multiple bonds, they have empty spots in their bonding structure that can be filled by adding more atoms, typically hydrogen. This is the opposite of the full stable structure of an alkane. We're going to focus on 2 major types of unsaturated hydrocarbons: alkenes, which contain a double bond, and alkynes, which contain a triple bond. The presence of these multiple bonds makes these compounds much more reactive than alkanes. They are key starting materials for many industrial processes, such as making polymers like polyethylene. First up in the unsaturated family are the alkenes. An alkene is an unsaturated hydrocarbon that contains at least 1 carbon-carbon double bond. This double bond consists of 1 strong sigma bond and 1 weaker pi bond. The presence of this pi bond is what makes alkenes so special. It's more exposed and reactive than the bonds in an alkane, which are all sigmas. The pi bond is the spot that is open for reaction, allowing for the addition of new atoms across the double bond. Alkenes also have a general formula. It's C subscript NH subscript tin. Notice that this is different from the alkane formula. For a given number of carbons, An alkene will always have two fewer hydrogens than its corresponding alkane, which is the direct result of the double bond replacing two CH single bonds. Let's look at an example. The smallest alkene has 2 carbons, because you need at least 2 carbons to have a double bond between them. So, for n equals 2, the formula is C2H4. This compound is called ethene, though you might hear it more commonly referred to by its older name, ethylene. Ethylene is a very important hormone in plants that regulates ripening, and it's also a major industrial chemical. So, to recap, alkenes are unsaturated, contain a carbon-carbon double bond, and have 2 fewer hydrogens than their saturated counterparts, making them more reactive. Finally, we come to the alkynes, the most unsaturated of the 3. An alkyne is an unsaturated hydrocarbon that contains at least one carbon-carbon triple bond. This triple bond is composed of 1 sigma bond and 2 pi bonds. With 2 p bonds instead of 1, alkynes are even more reactive than alkenes. They have even more empty spots available for reaction, making them excellent building blocks in organic synthesis. The general formula for alkynes reflects this higher degree of unsaturation. It's C subscript, NH subscript 2n-2. This means that for any given number of carbons n, an alkyne will have 2 fewer hydrogens than the corresponding alkene and 4 fewer than the alkane. It's truly undersaturated. Let's look at an example. Just like alkenes, alkynes require at least 2 carbons to form the defining bond. So for n equals 2, the formula is C2H2. This compound is called ethyne, but everyone knows it as acetylene. Acetylene is famous for its use in welding torches, where its combustion with oxygen produces an incredibly hot flame. It's a high-energy molecule. So, just to quickly review alkynes, they're unsaturated, feature a carbon-carbon triple bond, and are the most reactive of the 3 families. Okay, we've covered the 3 types. Now let's put it all together. Here's a summary table that helps visualize the differences. First, the key feature. Alkanes have only single bonds. Alkenes have a double bond, and alkynes have a triple bond. Because of these bond types, we classify alkanes as saturated, while alkenes and alkynes are both unsaturated. And the formulas clearly show this difference in hydrogen count. CnH2n plus 2 for alkanes, CnH2n for alkenes, and CnH2n2 for alkynes. This table encapsulates the core differences. A quick glance can tell you a lot about a compound's structure and reactivity. To solidify this, let's try a quick identification challenge. I'll show you a formula or a structure, and you try to figure out which class it belongs to. Ready? First up. What about C subscript 5H subscript 8? Take a moment to think about the general formulas. Does it fit CnH2n plus 2, CnH2n, or CnH2n2? It's an alkyne. If n is 5, then 2 times 5 minus 2 is 8. So this is a pentyene, like 1-pentyne. Next one. How about C subscript 3H subscript 8? This one is an alkane. It fits the CnH2n plus 2 formula perfectly. EMS3 gives us 2 times 3 plus 2, which is 8. This is propane, the gas we use in barbecues. One last one, let's look at a structure. What type of hydrocarbon is this? Remember to count the bonds. Since it contains a carbon-carbon double bond, this is an alkene. Its formula would be C4H8. Its name is 1-butene. So, let's wrap this up. Today, we've walked through the key differences between alkanes, alkenes, and alkynes. We started with alkanes, the saturated hydrocarbons with only carbon-carbon single bonds. Think of them as the stable and simple backbone of organic molecules. Then we moved to the unsaturated hydrocarbons, alkenes with their double bonds and alkynes with their triple bonds. These multiple bonds introduce reactivity, making these compounds excellent starting materials for more complex chemistry. Recognizing these bond types, single, double, or triple, is your most reliable tool for classifying these hydrocarbons. The general formulas are fantastic shortcuts for checking your work and for quickly identifying the class from a chemical formula. You now have a solid foundation for understanding the diversity and reactivity of organic compounds. Thanks for joining me.